Hello, welcome back to part 3 of this reading session of Broadband Silicon Photonic Directional Coupler using asymmetric waveguide phase control. So last time we have seen what is the working principle or philosophy behind achieving this broadband directional coupler, that too particularly for 50-50. Although researcher has designed splitting the ratio of 10 is to 90, 20 is to 80, 30 is to 70, 40 is to 60 and 50 is to 50. So these are the couplers, directional couplers, 1, 2, 3, 4, 5. 5 directional couplers have been designed for different splitting ratios. But the philosophy, as we know, that two symmetric and one asymmetric waveguide have been used, as shown in this figure 1, which is here. So this is L1, and this is also L1, which is a symmetric, and this is a asymmetric waveguide structure 15, which is working as a phase control section. Now, we have already come to know about this effective index distribution with respect to change in the wavelength. Then it's a mathematical representation is the relation between input and output. The relation between input and output, the electric field of the coupler can be expressed as this equation number 1. Thereafter, we come to know what is this coupling matrix, then this T ratio means through the straight through coefficient, then cross coupling coefficient K, and this propagation matrix P, and this is the PT, and then this is the contour map to determine this optimum length of L1 and L2 for 50-50 couplers. And this is the MDDT simulation for different wavelengths, say 1500 nanometer, 5050 nanometer, 1600 nanometer. Then we have seen the comparison among three methods is broadband digital coupler using 3D FDTD method, then broadband digital coupler with the transfer matrix method, that is called TMM, and third one is the conventional method, which has been shown with the green color curve for two modes, TE mode as well as for TM mode. So after that, now we will start today this fabrication. So our broadband digital couplers were fabricated using electron beam lithography on a SOI silicon wafer with 220 nanometer thick silicon on a 3 micrometer thick buried oxide layer. So it's about like this. 300. This box is 3 micrometer. Then up above we have 220 nanometer silicon waveguide. On this, by using electron beam lithography, this waveguide or the device has been designed, and after that 2 micrometer thick silicon dioxide. After that 2 micrometer silicon dioxide has been deposited for the protecting the layer using plasma enhanced chemical vapor deposition. So broadband digital couplers with various power splitting ratios have been fabricated. All of the couplers were designed to be characterized using an indirect measurement method. Figure 6a shows an optical image of a fabricated test structure. We characterized each of the broadband digital couplers by using it as the output recombiner of a 1 cross 2 MZI. So 1 cross 2 MZI is here, that is unbalanced MZI, and this is a L1 and this is L2. So L2 minus L1 give you delta L, and I think this is 300 micrometer. 300 micrometer. The different delta L is equal to 300 micrometer. So FSR is equal to lambda square divided by and G into delta L. So you can get this FSR. So this is the operating wavelength, and here, so FSR will give you the difference between these two peaks, free spectral range. So that is why this delta is very important. And G is the group index of the silicon material. Now, now figures okay. The where the input splitter was a balanced Y junction power splitter. So you can see here, this is the Y splitter. This one, this Y splitter, and this is the broadband district coupler structure. Okay, and this is the Y splitter. The asymmetric MZI has a delay length of delta L is equal to 360 micrometer. Grating couplers were used to couple light into and out of the MZI. So these are the grating couplers. This is the input grating coupler. These are the two output grating couplers. This and this. So input light is collected from the laser by this device, and it will be propagated through this way, and this Y branch will split the light into two halves, and this MZI will give the constructive and destructive interference based on this delta L. As we can see, this is the delta L. Based on this, it will give you constructive interference, and this is the destructive interference. At constructive interference, light will available, destructive interference, light will not available. And after that, your device under test, that is the broadband distributed coupler, has been used. So this is the input, and these are the two output grating coupler. And the difference between the gap between these two is 127 micrometer, which is the standard value. Were used to couple light into strip waveguide. Connecting the grating couplers to MZI were 500 nanometer wide by 220 nanometer height silicon nanowires. To calibrate the insertion loss of the input-output grating couplers, calibration structures having the same input and output configuration as the test structure were also fabricated, which is shown in the figure. So this second figure B is the for calibration purpose. You can see this is the grating coupler input and two are the grating couplers. So in order to just calibrate what are the insertion loss occurring because of the extra connection of these devices. So from there we can calibrate. Okay, take this. You can get the difference of now measurement of 50-50 broadband national coupler. To characterize our device, we used an Agilent 81600B tunable laser as the input source and both channels of an Agilent 81635A optical power sensor as the output detector. So this is the laser and this is the detectors. TE and TM mode fibers array were used to inject signal into the grating coupler and to collect the output signal from the two CGs. The patches of fiber within the fiber array match the 127 micrometer spacing between grating coupler or chip, making it convenient to align fibers to the input and output GC and to measure the output spectra simultaneously. Here we show and analyze the measurement results of 50-50 broadband distributed couplers. Figure 7a and b present the MZI output spectra for the TE and TM modes, respectively, in which the insertion loss introduced by the grating coupler have been calibrated out. The okay 7a 7b the MZI output spectra for TM mode, respectively, in which the insertion loss. The extension ratio, here we show the analyzed measurement result of 50-50 broadband distributed coupler. Figure 7 and 7 represent the output MZI output spectra for TNT boards. respectively, in which the insertion loss introduced by getting coupler have been calibrated out. The extension ratio here of an MZI refers to the power ratio difference of on a logarithmic scale of the two outputs when one is at the minimum and other is at the maximum. For the okay, so here extension ratio of MZI refers to the power ratio difference on a logarithmic scale of a two outputs. So we have two outputs. Basically, MZI is giving two outputs. So this and this. So when it is maximum and when it is the minimum, another one. So this one and this one. So at this value, this is the maximum and this is the minimum. So this is the y1 and this is the y2. So the extension ratio will refer to the power ratio difference on a logarithmic of two output when one is at maximum. So 10 log base 10. So suppose this is P1 and this is P2. So P1 divided by P2. So when one is at the minimum, okay, and another is at maximum, okay, or say is the maximum, this is the minimum, or you can say 10 log is 10 P2 by P1. For the T mode spectra shown in figure 7a, the extension ratio are greater than 20 dB over the 100 nanometer wavelength span from 1500 to 1600 nanometer. For TE mode, extension ratio is this. The excess loss of TE mode MZI circuit is less than 1 dB, which indicates the excess loss of a TE mode coupler is less than 1 dB. Now let us see figure 7a. Figure 7a is where? Where it is figure 7a? Yeah, this is figure 7a. So output 1 is blue color and output 2 is the red color. This is the power in dB and these are the wavelength. So when one power is this maximum or say minimum and another one is the maximum. Minimum, maximum, minimum, maximum. That will give you now here extension ratio, normalized splitting ratio. There is the extension ratio. Extension ratio is not given. The excess loss of T is 1 dB, which indicates that this one. For the TM mode spectra shown in figure B, the extension ratio exceeds 30 dB. This difference is more. Here, the difference is less in this, and this is difference is more. 0 to minus, okay, these are the range. So 30 dB, okay, and here 20 dB. So this line, if you can see, for most of the cases, this and this is for 30 dB. For TE mode spectra, this ER is greater than 20 dB over 100 nanometer wavelength range. From this, the excess loss of TE mode is 1 dB, which indicates the excess loss of TE mode is 1. And then 30 dB over the length of this, okay, 50-90 nanometer, 30 dB, 90. Okay, yeah, it is less here, from here to here, that is why even here to here. However, for this, all are coming. Okay, this is the observation. Now, and the excess loss of TM mode coupler is less than 0.7 dB. We attribute the excess loss to the sidewall roughness of SOI waveguide. As the T mode has larger overlap with the side wall of an SOI waveguide than the T mode. The T mode coupler suffers higher access loss. It needs to be mentioned that here the measured access loss also includes the loss in the MZI. Using the ER of the interference spectrum and the MZI output, we extracted the power splitting ratio of our coupler which are given by 20. This eta cross half plus minus half root of 1 minus 10 to power ERs divided by 10 minus 1 divide by 10 ERs then plus 1 whole square and beta through is this. The expected cross splitting ratio beta cross are shown in figure 7C and 7D. We use a plus minus 1 dB bandwidth and an average measured splitting ratio to evaluate the performance of the device. The plus minus 1 dB bandwidth is defined as the wavelength span over which deviation of the extracted eta cross are within plus minus 1 dB of the desired value. For example, the plus minus 1 dB bandwidth of a 50-50 coupler is the wavelength span over which its eta cross is within 63.1%, that is minus 2 dB to 39.8, that is minus 4 dB, while that of 10 to 90%, that is minus 10 dB coupler is within 12.6%, that is minus 9 dB to 7.9, that is minus 11 dB. As shown in figure 7C and 7D, the plus minus 1 dB limits are marked out by black dashed line. We define the average measured splitting ratio for a particular coupler as the mean of the expected power splitting ratios. Accordingly, as shown in figure 7C, the 50-50 T-mode coupler has a 88 nanometer bandwidth over the wavelength range from 1512 nanometer to 1600 nanometer, as well as an average measured splitting ratio of 46.1 to 53.9. As shown in figure 7D, the 50-50 TM mode coupler has a bandwidth of 97 nanometer from 1500 to 1597 nanometer and an average measured splitting ratio of 48.76 and 51.24. It also shows its best performance in the wavelength span from 1500 nanometer to 1590 nanometer, where the deviation of the extracted eta cross are within plus minus 0.15 dB. For the wavelengths above 1590 nanometer, the extracted eta cross of 50-50 TM mode coupler deviates from the simulation result. The reason is that our TM mode GCs show high insertion loss at wavelengths above 50-90 nanometer and they suppress the measurable ER. According to equation 7, smaller ERs indicate more deviation from 50-50 power splitter. At wavelengths above 50-90 nanometer, the ERs shown in figure 7b are limited by our measurement due to the insertion loss of the TM mode GCs, and thus the expected eta cross shown in figure 7d deviates from 50-50 power splitting. Our 50-50 TM mode coupler would appear to work better if the insertion loss of our TM mode GC are lower at the wavelength above 50-90 nanometer. In addition, please note that although the definition of the plus minus 1 dB bandwidth appears to be used for evaluating the 50-50 couplers, the expected eta cross of our 50-50 couplers are well defined, confined within a 1 dB bandwidth, that is from 0 dB to minus 1 dB of their design value, which are shown in figure 7C and 7D. The FDTD simulation results are also shown by the blue dashed line in figure 7C and 7D. 7C and 7D eta cross, okay, wavelength range plus minus 1 dB, 15 to this one, normalized power splitting ratio, okay, 50% T mode, okay, 0.5, 0.6, and 0.4, Eta cross is the red, blue is the FDT, and this is a measured. Measured one, this one, and this is the FDT method. Okay, and for TM mode, exactly. Okay, 1 plus minus 1 dB is within TE mode within 1 dB limit. Okay, for TM, okay, more bandwidth. Okay, below to this one is not satisfactory, but here above it is the limit. That is why 1512 to 1600 nanometer. So 78, 78 nanometer limit. Okay, and here exactly it's same 100 nanometer. Okay, so measurement result for the 5050 broadband digital coupler spectra of the MG for A TE mode and B TM mode. Extracted data of the broadband couplers for C TE mode and this extension ratio in B and the wavelength above 1590 are limited by the measurement due to the grating coupler insertion loss. Okay, so 7C and D. The updated simulation results are also shown by the blue dash line in section D. Good agreement is seen between the simulated and measured result when comparing the performance of the 5050 TE mode and T5050 TE mode coupler. The expected eta cross of the TE mode coupler is found to be less uniform than that of TE mode coupler. This phenomena will be discussed below. Measurement of broadband dash coupler with other power splitting ratios. I think we need again a break. We will come back and start from 3.3.